Light wavelength 400 nanometers, and we've already identified that as blue. Is incident on a metal surface. So that metal surface assumably contains many electrons within it. Those electrons are ejected from the metal surface with a maximum kinetic energy of this much. What is the frequency of the incoming light? How do you calculate frequency of a light? C equals F lambda. Speed of light, 3 times 10 to the 8th meters per second, equals the frequency, which we're calculating, times the wavelength, 400 nanometers, times 10 to the negative 9 meters. So the frequency, typically 10 to the 14th hertz. What is it this time? Sorry? 7.5 times 10 to the 14th hertz. So we haven't used any quantum physics, really. It was just old optics stuff. Sorry? I put lambda. Thank you. Frequency. What is the work function of the metal surface? Always a good place to start when you see that work function is the only equation which has work function. The kinetic energy of what? The electron that's left equals HF of the photon that came in minus the work function of the metal. So we have the kinetic energy. Do we want to go ahead and convert that to EVs, or can we keep it in joules for now? We can keep it in joules for now. That's okay. Just note that we're going to get our work function in joules when we come out of it. Kinetic energy, 1.1 times 10 to the negative 19th joules equals H. Which H? 6.625 times 10 to the... What is it? 34? That sounds right, 34. Joule seconds. Frequency of what? The photon which came in. 7.5 times 10 to the 14th hertz minus that work function. Some calculation there. 6.625 e negative 34 times 7.5 e 14. And then we're going to do 1.1 e negative 19 minus that number. And we get work function to be 3.8 times 10 to the negative 19th joules. Now the stopping potential for the emitted electrons, that is how much potential that it would take to stop the electrons after they are emitted from the metal itself. So it's not going to have anything to do with the work function. It's going to have to do with the amount of energy that the electrons left the metal with. Because that's the amount of energy that you need to take away from them in order to get them to stop. So the stopping potential is the voltage that's required to stop the electrons. Well, we know those electrons leave with 1.1 times 10 to the negative 19th joules of energy. Now this stopping potential, EVs, is far easier to do. So the conversion between joules and electron volts, 1 EV is equal to 1.6 times the negative 19th joules. And again, remember that 1.610 to the negative 19th joules, or number, 1.610 to the negative 19th, is the charge of an electron. So that's easier to remember. So if we have this many joules, we can divide that by 1.6 times 10 to the negative 19th joules per EV, and we get out of that the amount of electron volts we have. So 1.1 divided by 1.6 will give us 0.68 electron volts of energy. Now, according to the equation, energy equals QV, we can solve for the voltage required to eliminate this much energy. So 0.68 EVs of energy equals the charge, which we're stopping, which is V, times the voltage necessary. Voltage equals 0.68 volts. That is the potential that it is required to stop that electron from progressing any further. Basically, you're taking away the velocity of that electron. Now, the last part is relatively simple. Now, there's other ways to calculate momentum of photons and things like that, but momentum of particles which have mass is straightforward. P equals mv. So we need to first determine what the velocity of that particle is. Well, with this kinetic energy, it's not too hard. Kinetic energy equals 1/2 mv squared. 1.1 times 10 to the negative 19th joules of energy, as given in the problem, equals 1/2 times the mass in electron, 9.1, 10 to the negative 31 kilograms, v squared. Solve for velocity. 1.1 e negative 19 times 2 divided by 9.1 e negative 31, and square root of that value is 4.9 times 10 to the 5th meters per second. Take that value, plug it back in for momentum. There's probably an easier way to combine the kinetic energy momentum formula, but couldn't come up with it right away. So momentum of the electron is 9.1 times 10 to the negative 31 kilograms times the velocity, and we get a value of times 9.1 e negative 31, momentum of 4.47 times 10 to the negative 25th kilogram meters per second.